Welcome to Lecture 11 in our class on stochastic processes. We will conclude our introduction to the theory of martingales as promised with two applications which are kind of nice, I think. One is related to an application in economics, for instance, and has the name of the optimal stopping problem, and the other one is in mathematical biology and goes under the name of the Galton-Watson process. And as you will see further on, it is very up to date regarding the times that we're going through at the moment. Okay, let's start with the optional stopping problem. Let's jump right into the definition of the problem. So let omega fp be a filtered probability space, and let x1, x2, and so forth up to xn be a, in this case, finite sequence of adapted random variables. Then we want to consider the problem of optimal stopping as follows, namely, we want to maximize the expected value of the random variable, which is obtained by evaluating this sequence of random variables considered as an adapted process at a stopping time tau, and we want to maximize this within the class of all possible stopping times, which are stopping times relative to this given filtration f. This is what we understand as the optimal stopping problem. And of course here it's not assumed that the process x is Martingale or whatsoever, so no structural assumption on this process x is made except the assumption on adaptedness or measurability. And as an example, which is not at all a fictitious example, we want to consider the case of what is called an American call option on a stock. So we want to do this in the simplest model of a stock market dynamics. Here the problem is posed as follows. So suppose you have a sequence of IID Bernoulli random variables. With Bernoulli random variables, we want to understand a sequence of random variables xi or xi, which all can assume values each in -1 or +1. And the probability by which this happens is a certain parameter p in the unit interval. So xi k is the sequence of random variables which is independent, which are each Bernoulli with this probability p, and this is what we shall understand as the up or down movement of a certain stock, and the actual stock price at time k, which will be the underlying process for the bet or for the option that we want to formulate, is then defined as the sum of the up and down moves that the stock has made so far, when at time not at initial time the process starts at level S0. So Sk, let me say it again, is our very crude and very simplified first draft of a stock price dynamics model, which is the initial value of the stock or the initial price of the stock plus the sum of the up or down moves that the stock has made in the past up to moment k, when we actually evaluate the process now. So k stands for the time when we want to evaluate this stock price. So this is just a random walk. In effect, this is just a random walk with up and down movements with a certain individual up and down probability p or 1 minus p respectively. And the American call option, for instance, is now determined by a certain function, which is a payoff function of the stock price. So if Sk is the stock price, the bet on the stock price at time k is mathematically described by saying that the output function or the payoff function, or the actual payoff of the bet, if it is paid off at time k, is given by evaluating the stock price at time k by means of this outer function f, which is more or less just the identity function, but shifted and taken only the positive part. So f of t, that's the actual evaluation, or the, if you like, in physical terms, the observable of the stock sk, is the positive part of the shifted identity function, where k, that's the shift parameter here, is what is called the strike price of the stock, of the option. And by an American option, we want to understand that someone who owns this privilege, or who owns a certain contract, he is entitled to claim this amount of f applied to the sk at any time k of his choosing, of his or her choosing. Let me say it again. We assume that we have a certain underlying stock price dynamics, which is described here in this model by this simple sk dynamics. So that would be, for instance, our very simple model of a stock price dynamics for, say, the BMW stock price on the stock market. And now we do not want to deal with the BMW stock directly. We want to consider the case of a derived bet on the BMW price, which is formulated in terms of a certain payoff function, which is this tilted or shifted identity function, which is applied to the stock in order to generate an actual payoff. And this function xk is then the actual derivative or the derived payoff. But whether or not this amount is actually paid or not is an option to the owner of this privilege. So somebody granted to an investor the privilege to claim this amount of money at any time k when he or she wants to retrieve the money. And the filtration with which we want to work in this example is the filtration which is generated by the observations of the stock market dynamics. Okay, and now we come back to our problem of an optional stopping problem. The question is, what is a good stopping time? What is a good strategy, tau, for the investor to exercise, as we say, this privilege? So at any time, the investor can choose when she wants to retrieve the money, which at moment k is given by this function. And the investor can choose one moment of time when this privilege or when this claim shall be executed. And of course, there is better ways to execute the claims, and there are worse ways to execute the claim. And finally, whenever such a claim is executed or not, that shall be determined by looking at the history of the stock as it was observed so far, which in other words means that we are allowed to execute only by means of a stopping time. That's exactly the mathematical description of an investment or exercise strategy for this bet on the financial market, which does not look into the future, so which is based on information which is available to everybody at that moment of time. And now the game consists of choosing a stopping time, which in this case means choosing a strategy, which would maximize the expected value of the total payoff. That's the question, or that's the task that we want to address. This is an example of the general problem of an optimal stopping problem. So here the X process in our example that I had just discussed is this process of a possible output or possible payoff through an American call option, as we say. We will come back to this example after we developed this little bit of theory that we need in order to come up with a constructive algorithm how to generate an optimal stopping time that solves the issue. Okay, so for that purpose we need a few definitions and of course a couple of little lemmata that I shall present now. So in the situation as above, we have this reference process X, which can be executed at any time of our choosing. And we have this finitely many time points. We now inductively introduce a process which we denote by Z, and which will be constructed in a recursive fashion starting with the terminal time capital N, which is the latest time at which we will ultimately need to execute the order or the stop in the claim if we hadn't done before. Namely, we define the process Zn or Zn starting with terminal time N at terminal time just to be identical to Xn. So this is to be understood as follows. So if we haven't executed our X privilege before terminal time, then at terminal time ultimately we will need to execute, and the payoff we will get is then simply that payoff that is left at terminal time, namely Xn. At Zn minus, so for n minus 1, the Zn minus 1 is determined or is defined to be the maximum between execution at time n minus 1. There's a little misprint here, need to correct. And the conditional expectation of what we could possibly achieve if we did not execute at time n minus 1, but waited for execution for the terminal time when restricted to the conditional, when we consider the conditional expectation of this given the sigma field that we have at time n minus 1. So probably I should write that again. So Zn minus 1 is the maximum of the two options that we have at time n minus 1. Namely, either we execute at time n minus 1 and retrieve the amount xn minus 1, or we decide not to execute at time n minus 1 and play on. But in order to make a judgment whether playing on or waiting and executing now, whether that is a beneficial judgment, a beneficial decision, and want to make a judgment, we have to compare somehow the perspectives of Zn given the information that we have now with the option to execute now. And this comparison is realized by taking the maximum of the two functions. So Zn minus 1 represents the best we can do if we make the proper comparison between execution now and execution one moment later, but the execution of the privilege at one moment of time later, of course, needs to be evaluated by means of the information that we have at time n minus 1, which is our current time here. So therefore we compare xn minus 1 with the conditional expectation of the payoff that we can expect one moment of time later, but of course restricted to the information that we have today. Okay, that's the recursive formulation of how we define this Z process, and this Z process is then called the Snell envelope. So the Z process is called the Snell envelope of the process X. That's an important object in this optimal stopping problem, and we will use it in order to construct an optimal stopping time tau, which solves the problem. Okay, for doing that, we have a little proposition which says that Zk, this Snell envelope, is the minimal super martingale which still is dominating the initial process x in a pointwise fashion. Okay. First, why is Z a super martingale? Well, we write down just the definition. Zk, by definition, is xk max the conditional expectation of zk plus 1 given fk. Okay, so the maximum of two things is obviously bigger or equal than either of the two things. So this max is greater or equal than there's the conditional expectation, which is one of the two pieces which enters the max. But we already see that this yields the super martingale property. So in expectation, the thing that the Z process is a process which is decreasing in its trend. It has a decreasing conditional expectation, or it has a decreasing dynamics on average. That's how we would think of it. And why is it so? Well, if you look at the definition here, basically the Z process tries to represent the balance that we have when we have still some options left regarding the future and executing today. And so as time progresses, we have less and less options for hoping for, to say, or to have less and less possibilities to hope for a better evolution of the underlying randomness that would help us in the end. So therefore, the Zn thing is something which is decreasing in value, because the variety of options we have will decrease as time evolves, by definition of the Cn. Okay, so that is the verbal explanation why Z in fact is a super martingale. The actual mathematical reason or support of this intuitive understanding of the decreasing property of Zn has just been given. Okay, so that's why Z is in fact a super martingale. Now let's check that Z has this minimality property, that it is the pointwise, in the pointwise sense, the minimal super martingale, which still is above the X process. Well, first of all, by its very definition, we see that Z is an upper bound to the X process, and let Z tilde be now another super martingale which dominates the X process. And what we want to show is that Z tilde then must be necessarily bigger than Z, or at least not particularly less. So, okay, we do that, we prove that by induction, again in inverse time. Namely, at terminal time, Zn tilde is by assumption greater or equal to Xn, which by construction of Zn is the same as Zn. Now for the induction step, assume that we had shown that Z tilde is already greater or equal to Z for all indices J from terminal time up to time k plus 1. And we want to make sure that this is now also true for J equals k. So then Z tilde J by super martingale property of Z tilde is greater or equal to Z tilde at J plus 1 conditional on Fj. That's the super martingale property of Z tilde, which was part of our assumption. Now, for moment J plus 1, we already, by induction hypothesis, have proved that Z tilde J plus 1 is greater or equal to Z at J plus 1, and by monotonicity of conditional expectation, this also carries over to the conditional expectation. So therefore, Z tilde J is also greater or equal than the conditional expectation of Zj plus 1 given Fj. Also, by assumption on Z tilde, we know that Z tilde dominates Xj. So therefore, since it dominates both the conditional expectation here and Xj, it also dominates the pointwise supremum of Xj and this conditional expectation. But that was just our definition of Zj. So therefore we have that Zj tilde is no less than Zj. The next lemma. Tau that will be our candidate for an optimal stopping time, which is defined as the first time when this dominating super martingale actually equals xk. So let zk, we have just shown, or that zk is the minimal super martingale which still dominates. So therefore zk is a process whose trajectories really lie above the xk process, almost surely. And here we have the xk process. So that's the xk process and that's the zk process. And the first time that the two coincide, that's the stopping time, which is easy to see because it's just a minimum of stuff that we observe up to a certain moment of time and so forth. So that's the stopping time. And it will turn out that this is an optimizer, and that it is an optimal stopping time. But in order to convince ourselves, we have this first technical lemma, which tells us that the z process, which is a priori a super martingale, if we stop the z process by optional stopping, of course, we know it is a super martingale, but it is not only a super martingale, it is in fact a martingale. So the Snell super martingale envelope process is converted, or is actually, is in fact converted into a martingale by a stopping. That's not a contradiction to the optional stopping theorem, because it just says, the optional stopping theorem just says that if we have a super martingale in this case, and we stop it by a reasonable stopping time, then this gives super martingale again. But of course, the class of martingales is a subclass of super martingales, so therefore it's not a contradiction. Okay, so why is that true that this z tau is a martingale? Well, first, clearly, z tau is f-adapted. We had shown this before. Also, by definition of tau, tau is finite. That's just a technical remark, because at the latest, at terminal time n, the two processes z and x coincide, just by the very definition of z. Moreover, if we compare the increment, or if we evaluate the increments of the stop process, then we see that the increment, of course, plays a role only before the stopping actually kicks in. So the stop process has no increment if stopping hasn't yet occurred. So therefore, we see really something going on only when the stopping has already occurred. But if the stopping has not yet occurred, then this increment is in fact just the increment of the non-stop process. So either we have no increment because the stopping had kicked in, or we have an increment, and this increment then is the increment of the initial processes, just very much because the stopping hasn't yet kicked in. So therefore, this identity here is more or less a triviality. Again, the increment of a stop process is the indicator whether or not the stopping has already kicked in or not. And if the stopping has not yet kicked in, then the increment of the stop process, trivially, is the increment of the non-stop process, because the stopping has not yet kicked in. Okay. Now we want to prove that the stop process is a martingale with respect to the F filtration. So what we need to consider is, for instance, this conditional increment. Given the sigma field Fk, when we consider this stop process and its increment in the time step from k to k plus 1. Now, if we insert this formula that we had just discussed regarding the indicator on whether or not the stopping has kicked in or not, then we see that this increment by the so here's a little bit of an argument here. Namely, if the stopping time has not yet kicked in, what does that mean for the stopping time that we actually discuss here? Well, the stopping time here kicks in once this super martingale equals the once the super martingale equals the X process. So if the stopping time has not yet kicked in at time k, or at the earliest at the time k plus 1, this means that at time point k, there was actually still a real distinction between the Z process and the X process. And what is the Z process as compared to the X process? The Z process is just the conditional expectation of the ZK plus 1 if that number is still strictly bigger than the X process. So therefore, if the stopping time is really strictly bigger than k plus 1, then the ZK, which is this maximum thing, must be in fact the other part of this maximum. So in the maximum operation, the non-xk part must have been the bigger part, which therefore allows us to just replace this zk by the definition, in this case, which is just the part in the maximum which is not the xk. Okay, now that was this little step here, and the next thing to observe is that whether or not the stopping time has kicked in at time k plus 1 or not, that is something that we can observe already by watching the whole evolution of the processes up to moment time k alone. Because we can distinguish, or we can make a decision, or observe whether the stopping time has occurred at time k at the latest or not, by measurability or by adaptedness, by looking at the time k at most. So therefore, whether or not tau is greater or equal to k plus 1 is determined by looking at everything that happened up to time k alone, which means that this indicator is an indicator as a function which is measurable with respect to the sigma field on which we compute the conditional expectation. And hence, we can take this product or this factor out of the product inside the conditional expectation and write it just in front. Okay, now everything that's left inside the conditional expectation is very obvious and clear, because it's just the difference of the zk plus 1 process conditioned to fk minus the zk plus 1 process, and the whole thing is again taken into the conditional expectation. So this is the difference of a projection, of a projected thing towards the non-projected thing after we take the projection, and that's a 0. Hence, we have seen that this stop process is in fact the Martingale. This we can now convince ourselves that this tau is in fact an optimal stopping time and solves the problem. Namely, it maximizes all expected values among the collection of stopping times, which are f stopping times, and the corresponding number, the corresponding optimal value, is given by this Snell envelope evaluated at time 0. That's the actual stopping time, optional stopping time theorem, which is written here. Okay, why is that correct? Well, if sigma is any stopping time, then since z, the z process, is a dominating process just by monotonicity of expectation, the expectation of x sigma is less or equal than the conditional expectation of the random variable, which is bigger, which is the z. Now z is, as we had seen, a super martingale, so it's something which is decreasing in tendency, and therefore this expectation here is less or equal than the expectation of the z process at initial time. But at initial time, we want to assume that the sigma algebra here is taken to be the trivial sigma algebra. This is just the z naught process, so there's just this constant at time 0. So for any stopping time, this conditional expectation, this expectation is no bigger than the Snell envelope evaluated at time 0. Now, if we pick our special stopping time, x tau, and evaluate x tau there, then by definition we know that x tau in value, or just at time tau, the x process, by the very definition of the tau, is equal to the z process at time tau. because tau is the first time when z and x coincide. Okay, z tau, we can write this thing also as the stopped process z, the stopped process of the super martingale z evaluated at the terminal time, because tau is no bigger than n anyway, so the info of tau at n is tau, so that's just another way to write this quantity. But now we know that this z tau, the stop process, is a martingale, which in particular has has constant expectation, so this expected value is the same as the expected value at initial time. And of course the z process, even if we stop it or not at initial time, is just the z process at initial time, which is easy enough. So therefore we see that we have one stopping time tau, which achieves this upper bound z0, which is universal for all stopping times. So therefore this tau must be an optimal stopping time. So this gives this optimal stopping theorem gives a constructive way how to generate one proposal for an optimal stopping time. There are examples, many examples in fact, when there's various stopping times which would do the job, which are optimal, but this is a very concrete and very explicit way how to generate a proposal for an optimal stopping time, even if you have no intuition whatsoever about the concrete problem you're dealing with. So let us therefore sketch how we can use that in this example of the American call option that we had discussed. And let us assume, to be very simple here, just the case when we have 2 or 3 moments of time when we have a decision to make. So terminal time is 2, which means that we set up the whole stock market, or we initialize the whole problem at time equals 0. Then there's one time step to t1, which is the first time step, and then there's a terminal time step. So effectively, we have to make a decision whether we execute immediately at 0 time, we execute at time 1, or we wait until terminal time. Okay, so terminal time here is 2. Now we just conduct the whole algorithm in this particular case. So we have a process x, which is this aggregate up and down process. So it's the correction. It's not the x process, is the s process that stands for stock. Here we can have a misprint. So s stands for stock, right? So that's this combined up and down process. And the x process describes the payoff we get at the respective time if we execute our claim at that moment. Okay, and now we will simply just execute this algorithm, and the algorithm is executed by computing this Snell envelope first. So that's a concrete computation you have to do. Okay, and it starts with initializing the Snell envelope at terminal time, which, again, let me say it again, corresponds to the payoff you get if you decided to wait on until the very end of time. So if you decide with the execution until the very end, then at the end you get this amount. F, that's the outer function. Here is this shifted, truncated identity function applied to the stock price at time 2. Okay, that's clear. Then Z1, that's the Snell envelope 1 moment prior to that, is defined as the maximum of the payoff you get in case you choose to execute at time 1, which is x1, or the conditional expectation of the payoff you get if you decide to execute a moment later, or in other words, to play on. So it's the conditional expectation of S to a given F1. Okay. Now, the unpleasant thing sometimes is to actually compute this conditional expectation. I tried to do it in this particular case here for your benefit, and in the competition below I will assume that this parameter p for up movement is less than a half. So the stock has the tendency to go down over time. Okay, so let's compute the conditional expectation of Z2 given F1. F1 here is the sigma field which is generated simply by the stock at time 1, which is the same as the sigma field generated by the psi 1. Okay, so we have to compute f of s of Z2, the conditional expectation of Z2. Z2 is f of S2, so it's the conditional expectation of f of S1 plus psi 2 given psi 1, x1, which is like psi x1. Now, if we know what x1 is, which is the same as knowing what psi 1 is, then there's only ambiguity with respect to psi 2, so psi 2 can then assume two different values, plus 1 or minus 1. That's written here, and those two things happen with probability p or 1 minus p. That's the conditional expectation we need to evaluate. So therefore Z1 is the maximum of the payoff for S1, or the conditional expectation of the payoff for a later moment of time. That's written here. Now, if you evaluate these numbers, then it's a little bit of work to consider different cases, but you will convince yourself easily that the maximum of these two numbers, if p is less than a half, is f of S1 if S1 is greater or equal to k. So let me say it again. So that's the payoff function here. Here's this number k. So if S1 is greater or equal to k, then f of S1 will be bigger than this convex combination of the other possible payoff values that you obtain when you take the shifted or the payoff at a later moment of time, which then also accounts for the additional jump of up and down caused by the next evaluation of the psi random variable. And if the stock at time 1 is less or equal to k, then the second component is the bigger one. Because simply if S1 is less or equal to k, then by the definition of the f function, this f value will be 0. In anything which is not 0 and which is possibly positive is favorable over to the nothing that you have in the first component if S1 is less or equal to k. Okay, so therefore we have this representation of this Z1 function, namely if S1 is greater or equal to k, then the Z1 is f of S1, and if S1 is less or equal to k, then the Z function or the Z random variable is this convex combination of the two possible odd payoff values. And finally, you can also compute the Z0 value, which is the maximum of f of S0, just by the definition, and the expectation of Z1. Now let us assume for simplicity that the S0 value is just the level of the stock at time 0, which is a datum of the problem, is below the number k. So assume for a moment that k equals 3/2 and S0 is initialized to be 1, which means that this payoff function f, which is colored here in red, at the initial, so this would mean that k here has the value of 3/2, and we want to start the stock model at a location which is really below this level. So that would be a 1 here. So and therefore, obviously, f of s naught here is just a plain 0. So anything which is not 0 is better than this 0 value. And therefore, we get just the E of z1 as the maximum. Okay. And this then tells us what? So the E of z1 obviously is bigger, which is strictly bigger than z0. So that tells us that tau equals naught is not a good choice for the stopping time. And we see that the z1 random variable, it coincides with the payoff function x1 in case when s1 is greater or equal to k. And this means that we execute at this moment of time. But if s1 is not bigger or equal to k, then we wait and execute at the later moment of time. So this is then ultimately the answer to our optimal stopping problem in this special case, or in this case of this American stock, in this American option. And it's quite intuitive in the end, and it would be the answer that you would have come up even without all this little bit of theory regarding the optimal stopping problem. It just says, okay, if at time 1 we are already in the situation that the stock really pays off, then we execute the option. And if at time 1 the stock level is so that we do not really benefit, then we actually wait until and give it a chance a little moment of time later. So that would be obviously a very obvious choice of a strategy. And by this theory that we have just, a little bit of theory that we have just developed, we now also know that this is in fact an optimal choice of an execution time. So this optimal stopping theorem is now the basis for many nice exercises that you can formulate and many nice computations you can do. And this recursive computation of this Snell envelope, that can be quite clumsy, but nevertheless it's a nice game to play. And I want to provide one more example for this. Namely, for instance, suppose you play a game where you are tossing a coin, but here it's not a coin with 2 outcomes, with 3 outcomes. So you have a uniform random generator which generates numbers 1, 2, or 3, and you can generate this 3 numbers. You can generate numbers up to 3 times. So you can use this random number generator up to 3 times. That's the game that you can play, but you can choose not to generate it, or not to use it all the 3 times. You can just stop producing new numbers if you want. And the payoff of the game will be just the number, just the sum of the sampled numbers, provided the sum does not exceed 5. So in a way, this is a variant of the blackjack game, right? You collect cards and the value of the cards is aggregated, provided the number does not exceed level 21 or something like this. This is the blackjack game. And here I'm basically doing a similar thing as the blackjack game, but here I have card values 1, 2, 3, which can occur with equal probability, and I have up to 3 cards I can collect, and the number, the critical threshold is here in the number 5. And the question here is obviously, what's a prescription, what's an optimal strategy such that on average you obtain the maximal amount of money if your payoff, as I just said, is the sum of all the numbers which you generated in these numbers of rounds that's at your disposal, provided the number does not exceed the total value 5. So we introduce xk which is just the number as the sum of the chosen of the sampled numbers. So for k equals 2, this is just the sum of the first two sampled numbers, and we define x naught to be 0. And the output of this game, that's the sk random variable, is xk, is just the aggregate number of the aggregate of the sampled numbers, provided this aggregate is below 5. And you have to choose now, or you have to define now a strategy which would tell you when are you satisfied, when will you stop asking for the next number to be generated. Okay. Here in this game you can just, let me say it again, here in this game you can just pick the first random number, look at it and decide whether you want to play on. Then you pick the second number, you sum the two numbers up, and then you have to make a choice whether you want to play on or not. And the question is, what's an optimal choice for a strategy when you should probably stop asking for the next number to be generated? And this is just another case of an application of the optimal stopping theorem in a way, which we had just discussed. Namely, we do it as before. We introduce this Snell envelope Z, which at terminal time, which is 3 here, is just defined to be S3, because S3 is the payoff function. And at Z2 then, in time 2, Z2 is the maximum of S2, and the conditional expectation of S3 given F2. Now, by this constraint about the total sum being no bigger than 5, you can compute now the possible conditional expected value of S3 given F2, which means that you have seen the first two numbers which are generated, which means that you know what x2 is, and depending on x2, you can then compute the conditional expectation of S3. For instance, if x2 is 2, so the first two numbers in sum are 2, which means both were 1. So then what's the expectation of the total win or loss after that? Well, you know that you have 2 already, and what you add is the mean value of all the future, namely outputs, which is 1, 2, or 3 with equal probabilities. So the mean value of this is 2. So you have 2 plus 2 as the expected value, which is a 4. If the first two numbers together produced a 3, then the conditional expectation of the total payoff of the game, if you play also the third round, is that with probability 1/3 you generate a 1 in the third round, which together with the 3 that you have collected so far produces a 4. That's the output with which you have with the probability 1/3. Also, with the same argument, you have an output of 5 with probability 1/3, which corresponds to having a 2 in the third round. But if you have a 6 in the third round, that already produces a total aggregate of 6, which is above the threshold, so you see nothing as an output, and hence you gain nothing in this case. So the total expected value for the whole output is then this two numbers, 4/3 plus 5/3, which is the 3, of course. And if, likewise, if the first two numbers together generated a 4, then there's only one possible result for the third round, which generates some output at all. That's the result. One which occurs with probability 1/3, and that generates the total output of 5. So that's the conditional expectation of the payoff if you take into consideration the results that you have observed up to time t2. And this needs to be compared with the output that you obtain if you just stop playing in the round 2, which is just the aggregate number, provided that number is no bigger, or is no bigger than 5. And you see that this conditional expectation term is bigger than the S2 part, only if the x2 function is 2. So, and if the x2 function is 3, then the two are coinciding, and if the x2 is 4 or 5, then it is better to take what you got so far. So S2, this term here, is bigger than this term, just by comparison of the two functions, if the aggregate result of the first two rounds is between 3 and 5. Where one should say that if the aggregate result is 2, if the aggregate result is 3, so if x2 is 3, then it does not make a difference whether you play on or you decide to stop. And this is just written here once more, that this conditional expectation is bigger than S2 if and only if, or if the result of the first two rounds is below or equal to 4. Obviously, it's better, or it's not good, to end the game only after the first number is generated. It's always a good idea to play a second round, so therefore tau should be greater or equal to 1 anyway. So you should take at least one sample. And at the end, this tells you that the stopping time, the optional stopping time, is given by this rule. So when the first two rounds gave a result which is smaller or equal to 3, then it is advisable and preferable to play a third round. And if the first two rounds gave a result which is above the level 4, then it's better to stop at this time. And here I think I made a mistake, so that's a 3 here. I need to write a 3. And here I need to write a 2. So let me say it again. The optimal stopping time, or one optimal stopping time, is obtained by the following strategy. If the first two rounds, so you sample 2 rounds, you go 2 rounds under all circumstances, and if the results of the first 2 rounds sum up to a number no bigger than 3, then you go for the third round. And if the first 2 rounds sum up for a number 4 or higher, then you stop and you are satisfied with what you got. That's the optimal stopping time in this game. The next nice application of this Martingale theory is the Galton-Watson process, which is a mathematical model for the family tree, or for the number of members of a generation of a certain family. You can also, of course, given the situation that we're living in at the moment, you can also tell a story of people who carry a disease and who infect this disease to other people. And at each moment of time, you ask how many people do you have in that generation of infected patients. To model this in a mathematical model, we will, here in the Galton-Watson process, we assume that we are given a family of double-indexed random variables, psi jn, which are all identically distributed and independent, and which assume values in the integers, including 0. And these two different indices have a different role. So J stands for the individual J in the n plus first generation of a given family, say, or generation in a given succession of infected patients. So psi j with index n plus 1 is the jth individual in the generation n plus 1. So it's the number, or it's the psi j n plus 1 is the number of offspring that the individual j, which is in generation n, has generated. So psi j n plus 1 is the number of children that individual j, which belongs to generation n, will have in generation n plus 1. And each individual can give rise to a next generation only once. So psi j n plus 1 is the number that the individual j, which was a member of the nth generation, will have in generation n plus 1. And this individual can have children only once in its entire lifetime. And we want to think of the entire population, which is measured in generation n. So we want to think of the whole family tree, starting with an individual 0, or with the patient 0, if you like, which is one individual. And then this one individual in generation number 1, so this one individual, if you like, is the generation 0. And this one individual then has a certain amount of successors or children or infected patients that this individual 0 has infected, and this number is described by the random variable psi 1, 1. Okay, so that's the number of children in generation 1, or the number of members of generation 1. Now, the number of members of generation 2 is given by summing over all members of generation 1 the number of children that each of those generation 1 individuals has generated. And each of those numbers are given by the random variables psi j2. And you carry on in this fashion inductively, which means that in generation n plus 1, the number of individuals you have is given by summing over all members of the generation n the respective amount of children that this corresponding individual has had. And that's given by, for each of those individuals j, the number psi j n plus 1. Okay. And the question we want to ask is, does this family get extinct or not? Does it get extinct with probability 1? Or can we say anything about the extinction probability of this family? So, in terms of disease, we can ask, is it so that this disease will die out or not? And what's the condition on these random variables, psi j, which are the actual datum? What are the conditions on the random variable which will guarantee the extinction of this family? And of course, an important parameter here is the expected value of children of one characteristic or typical individual. So mu, that will be a very important parameter, is the expected number of children that one such individual will have. And if that number is below 1, we call that the whole model subcritical, or we call it the subcritical case. If mu is strictly positive, correction strictly above 0, we call it supercritical. And if mu equals 1, we call it the critical situation. Well, in the discussion we have regarding this coronavirus at the moment, mu is basically this R value. It's just the reproduction rate, the mean reproduction rate. So if R is below 1, we have mean production, which is below 0. So and the statement will be that if we are in a subcritical case and even in a critical case, we have extinction with positive probability 1. And if mu is positive, then we have a more or less exact representation or exact description of the probability of getting extinct. Okay, and we want to apply some Martingale arguments in order to give an answer to this question in the 3 different regimes. And for a Martingale argument to be applied, we want to introduce a filtration, namely the filtration of the sigma field at index n is the sigma field which is obtained by all the offspring variables of all generations up to time n. Okay. And now we want to argue that this total number of members of a population is a martingale if we properly normalize. And to see this, we compute now the conditional expectation of the size of the population at time n+1, given the information on the offspring up to time n, up to generation n. Now, by the definition of this Zn process, this random variable Zn+1 is just the sum of this called individual offspring variables given Fn. We just can take the conditional expectation. So this sum, which is taken up to the level Zn, can also be written as a sum with respect to all j, but where we have to introduce or put in this additional indicator. Now we exchanged expectation and the sum. And we finally see that this question whether or not j is less or equal to Zn is a question which is related to the realization of the offspring up to time n. So therefore it's a random variable which is measurable with respect to the sigma field Fn, so therefore we can take it out of the conditional expectation and put it in front. And what remains is the conditional expectation of psi j n+1 given Fn, but psi j n+1 is independent of Fn. The question how much an individual in the generation n+1 has offspring is independent of the offspring of the previous generations. So therefore the conditional expectation is just a plain expectation, and that was the mu. And so we are having this constant factor mu in this sum, which we can take in front, and the sum just counts the number of members in the generation Zn. And here again, yes, so that's just right. So we see that the conditional expectation of Zn plus 1 given Fn is Zn times mu, which in other words says that if we make a little deductive argument that the process Xn, which is obtained by taking Zn divided by mu to the power n, that this is a martingale with respect to this filtration. So here we have to divide by a certain power in order to obtain a martingale. Moreover, since Zn is non-negative and mu n as well, this is a non-negative martingale, and the expected value of this non-negative martingale, which is what we have seen, is just constant, is 1. And obviously, since it is a non-negative, this is the same as the expected value of the positive part of this martingale, and therefore we are in a situation when we can apply the dupe convergence theorem, because we have a martingale, which is in particular a submartingale, which is non-negative, which has uniformly bounded expected value of its positive part. So therefore, by dupe convergence, we know that there is stabilization of trajectories, which means that xn for n tending to infinity converges to random variable x infinity almost surely, which is a random variable. And this, in other words, means that this Zn process, which is the xn, but without the mu n denominator, so therefore Zn behaves like mu n, so it's like behaving like an exponential process, and the constant of the exponential behavior is this x infinity random variable. Okay, and we want to address, as I just said, the question whether or not this population gets extinct or not. And for that purpose, we introduce what is called the extinction time. So whenever this population is down to 0, then it will not revive. It will just stay to be 0 because there's no more offspring. In order to have offspring, you need at least to have one individual in the whole population. But there is no individual, there cannot be any offspring. So Zn equals naught. That's certainly a moment when there is no populations, they got extinct, and there will be nothing in the past, in the future. And the first time when that happens is what we call the extinction time of this process. The first proposition here is that if the mean offspring, mu, is strictly smaller than 1, then this extinction time is finite almost surely. So in the subcritical regime, the family gets extinct almost surely in finite time. Of course, it's a random time. When this extinction happens will depend on randomness, but the population will get extinct in finite time eventually. Okay, we show this by considering the martingale that we had just seen before. If we do the Zn process divided by mu n, and we have seen that this is a process which has expectation 1. So therefore E of Zn is just mu to the power n, which by mu is smaller than 1, converges to 0. Also we know that Zn is greater or equal to 1 wherever it is positive, because Zn is integer valued. So therefore the probability of Zn being greater or equal to naught by Chebyshev inequality is, or a version of Chebyshev inequality, is bounded from above by the expected value of Zn alone, where Zn is positive. This is a very simple way of Chebyshev inequality, in fact. But this is the same as the expected value of Zn, because whenever Zn is strictly 0, this does not contribute to the expected value anyway. And this, by what we have just said, is mu to the power n, which converges to 0. So therefore, the probability of Zn being positive converges to 0. Now, psi being infinity is, in terms of events, in terms of events the same as saying that this is the collection of all trajectories which lie in the intersection of those trajectories which are still alive at time n. So this is just a simple logical equality here, that psi equals infinity. So extinction time infinity means that these are all those trajectories when we have population at all times. But this is a monotone sequence of events, so therefore by monotonicity of probability, this is the same as, so the probability for this, I'm sorry, there's again a misprint here, which I need to correct. So the probability of all this is the probability of this, but this is the probability of an intersection of events which are monotone, so therefore this is the same as the probability, as the limit of the individual probabilities, and we have just convinced ourselves that the limit of all these probabilities is 0. So we have proved the claim. So let me say it again. We have just convinced ourselves that when the Galton-Watson process is subcritical, so when the mean offspring is strictly smaller than 1, then the family gets extinct in finite time almost surely. The next consideration deals with the case when we have a critical Galton-Watson tree, or critical Galton-Watson process. Namely, mean offspring is 1, but the variance is strictly positive, so we have really a random process. Then we get extinct in finite time almost surely. How do we prove this? Well, mu equals 1 means that already the z process is a non-negative martingale. So before we considered the process xn, which was zn divided by mu to the power n, and showed that this is a martingale, but if mu equals 1, then this ratio has no effect, so it's just the zn process, which is already a non-negative martingale. And by the same considerations as before, we have stabilization of trajectories, so we have convergence by Convergence Theorem to a random variable z infinity, almost surely. But Zn is an integer valued process, so an integer valued trajectories can converge only if they become constant almost surely. But this means that psi is finite almost surely. Why? Well, if psi is not finite almost surely, and we have stabilization, well, for all trajectories we have stabilization towards some random point in finite time. But the Zn process is easily to see that the Zn process is also a Markov chain. And since we have assumed that the variance is strictly positive of the offspring, this is a Markov chain which has only one absorbing state, which is the absorbing state 0. The Duke Convergence Theorem tells us that the process almost surely ends up in an absorbing state, but there can be only one absorbing state, which is a 0 state, due to the assumption that we really have variance, positive variance. So therefore, the only state which can be assumed in finite time almost surely is in fact the 0 state, and this is extinction in finite time. We now want to treat the supercritical case, which in a way is the most interesting one, and this we will treat without Martingale problems, but using generating the argument of generating functions. So consider the supercritical case, and let pk be the number which is the probability that we have for one individual exactly k children. That's just a way to describe. So in fact, it's just pk is just the distribution. It's just the law of this offspring random variable. Xi1 is also called the offspring random variable. And we introduce now this moment generating function for this offspring random variable, which is the expected number of s to the power psi 1, 1, where s is a free parameter. So for any free parameter s in the unit interval, we compute the expected value of that number s taken to the power psi 1, 1, where psi 1, 1 is the random variable which we want to consider. It's just this offspring random variable. This is an integer valued random variable, so this s to the power psi, when s is a number between 0 and 1, is well defined. And the output of this expectation is a number between 0 and 1. And if we just write out this expected value in terms of the law of the random variable psi 1, 1, we obtain this expression. It's just this sum. This sum is, or this function is called the moment generating function. Okay, let's collect some properties. So phi at naught, when we insert s to be naught, then this is just the probability for the offspring to be 0, and that's a number strictly less than 1. Then we want to compute the derivative of this function. So the derivative of this function, if we want to write that out, obviously, so phi prime of s, if we want to write that out, is the sum, the zeroth order term disappears, so it's k equals to 1 from k times s to the k minus 1 times pk. And if we evaluate this at s equals 1, we get this term here, because all these s powers are equal to 1 in this case, and this is just the expected value of psi 1, 1. That's the number mu, which is assumed to be strictly bigger than 1. So phi prime at 1 is mu strictly greater than 1. Likewise, phi prime of 0, by a similar computation, is the probability that the offspring is exactly 1, and this is in the non-deterministic case a number which is strictly below than 1. And finally, we compute the second order derivative of this function phi by a similar computation as above, is the sum of all these s powers when k is greater or equal to 2 of k times k minus 1 times s to the k minus 2 times pk. And this is a number which is strictly positive if the random variable phi, again, is not deterministic or not equal to, and if the expectation is greater or equal to 1, right? It's strictly greater than 1. So hence, we see that this function phi is also strictly convex. And finally, the value of phi at 1, if we insert s equals 1, then this s power to something is just a 1, so therefore phi of 1 is 1. So if we draw the graph of the phi function, it will look qualitatively like this. So this is the graph of the phi function as a function from the unit interval into itself, into the unit interval. So at s, so that's the s here, at s equals naught, phi of naught is less than 1. At phi of 1, at s equals 1, the function is equal to 1. It is strictly convex, and it starts with a derivative which is below 1 at initial time s naught, and it's strictly above 1 at time s equals 1. And by an analytic lemma from one-dimensional analysis, you convince yourself that this means that there must be a unique interior fixed point of this function phi. which means that there is a unique point rho where the function phi meets the identity function. So there's a unique function, a unique point rho inside the unit interval, strict interior point, where phi of rho equals rho. So it's a unique interior fixed point. And this is also a stable fixed point, which means that when you start an iteration which is constructed by using the function phi, an iteration on the unit interval, and you start, for instance, from a p naught, then, which is in the strict interior, then this iteration produces a limit which coincides with this fixed point rho. Right, so we have a local contraction, and this converges to this interior fixed point. That's a lemma from one-dimensional analysis, which you apply here, and which you can apply because the function phi satisfies these assumptions. Okay. Now we want to conclude that in the supercritical case, that's the terminal and final conclusion of this session today. We want to conclude today that in the supercritical case, the probability of extinction is exactly given by this parameter rho, which is the fixed point of this generating function. Okay, why is that true? Well, we introduce an auxiliary quantity, which is theta n, which is defined to be the probability that the extinction time is no bigger than n. So it's the probability that the population gets extinct by the time n at the latest. And of course, this is equivalent to saying that Zn, that the size of the population at time n is 0. Now, what's the probability that the population is extinct already at time 1? That's p naught, because we have individual 0, which has offspring. And if individual 0 has offspring 0, then already the individual 0 is the only member of the entire family. And that happens with probability p naught, which is the probability of having 0 offspring for any individual. Now, what's the probability of having no population in generation n if we had k members of the first generation? Well, the evolution of the populations, of the subpopulations, which are the successors of an individual, of one individual, they are absolutely not related to the size and the future development of the individuals which follow another representative somewhere else in the family tree. So the different branches of the different families behave in an independent fashion. This is what I wanted to say. So therefore, the probability to get extinct for the entire family in the nth generation, provided in the first generation we had k individuals, is the same as having 0 individual, 0 population in the n-first population, in the n-first generation, taken to the power k, which accounts for the k individual subfamilies which behave in an independent fashion, departing from each of the individuals in the first generation. So once more, if we ask for the probability of having extinction on the nth generation, given that in the first generation we had k individuals, this is the same as saying that all the subfamilies which were created by each of the individuals in the generation number 1, that all these subfamilies are extinct by time n. But all those subfamilies behave independently because they don't interact with the other subfamilies. And this question then is a question which extends over a time period of n-1 generations. This quantity for an individual family starting from an individual number 1 or 0 at initial time to get it extinct, this is the quantity which we call theta n-1. And therefore we see that the probability of getting extinct in generation n, when we assume that in generation 1 we hit k individuals by independence, is the same as getting extinct in n-1 generations starting from one individual times in the power k for these k independent events. So therefore this probability which we had written here, this conditional probability here, is the theta n-1 parameter, so the probability of getting extinct in n-1 steps, taken to the power k. And hence, if we ask for the probability to get extinct at time n, we can then decompose this probability into a set of conditional probabilities, where the conditional probabilities are just the quantities which we have just discussed. We have convinced ourselves that this number here, for each k, which is the possible number of offspring of individual number 0. So this is this number here that we had just discussed. This is theta n-1 to the power k, and this probability here was the pk. Was the probability that we, in one offspring, we have exactly k children. And we see that this total expression we have here is exactly the generating function phi evaluated on the parameter theta n minus 1. And hence we have the recursive formula that the number theta n is given by applying the generating function phi to the parameter theta n minus 1. Hence, if we introduce the parameter theta, which is the limit of this theta n recursion, by our one-dimensional analysis lemma, we know that this is the parameter rho. But this is, by monotonicity of events, just the probability. There is a little mistake here. Sorry, I need to correct again. By monotonicity of events, this is, and continuity of probability measure, this is the same as the probability of the union of all these events of getting extinct in finite time. And this is therefore just the probability of getting extinct in finite time in a straightforward fashion. So we see that this theta, which is then the rho, is exactly the quantity that was in the claim. So to sum up, we see that in this Galton-Watson model, which is the most fundamental model of mathematical biology in this spread of disease, when you have no spatial component and no geography or something like this, is just a very straightforward first sketch of a genealogical or disease model. We distinguish three different cases, namely the subcritical, the critical, and the supercritical regime. In the sub and critical regime, we have shown that the family gets extinct almost surely in finite time. And in the supercritical regime, there is a distinctive number rho, which is given by the specifics of this offspring generation distribution, which is the interior fixed point of the generating function, which is the probability that we get extinct in finite time, which is a positive number in general, because it may happen even in the supercritical case that by randomness the family gets extinct even if we have supercritical offspring. So this concludes the second example that I wanted to present, and this also concludes our treatment of martingales as a standalone subject, and we will now move on with more advanced subjects in a way with Brownian motion and later with stochastic calculus.